Hello, guys. Am I audible to you? You can reply in the chat section if I am audible. Okay, thank you. So, hello everyone. It's great to see you guys joining early. Just stay tuned. We'll be starting shortly. Let other members also join. Thank you. Guys, we'll be starting in some time. So, are you guys all excited for this session? You can just type in the chat section. We'll be starting in some time. Okay, Himanshu, we'll just share the link with you and you will get all the details, like further details of all the webinars there on that link. We'll be sharing it in the chat section shortly. Guys, you can check the details of the upcoming sessions in the chat section. We have shared that. You can have a look at it. Hello, Anant. Am I audible?
Yes, you're audible. Is this Siddharth?
Yeah, this is Siddharth. Good evening. I hope you are doing great.
Yeah, I'm doing good. Good evening to you too.
Yeah, thank you. So it's my privilege to be the host for this session. And like we'll be starting shortly.
Okay, sure.
Thank you. So thanks guys for joining in. Stay tuned. We'll be starting shortly. Yeah, so hello everyone. Welcome to another session of DataHour series. We'll be starting in just 5 minutes. Till then, let's get to know each other. Actually, we have put up a poll that contains two questions about your location and experience level. So kindly answer the questions in the poll and I'll be waiting for your response. Kindly do that, please. Thank you. Welcome, guys. You all can just fill up the poll, which is live. Guys, please fill in the poll. All the people who have joined just now, you can fill the poll. Please fill the polls as we are just about to start. Hello and welcome everyone to another session in the DataHour series. I hope you all are very excited for this session. We are thrilled to be here with you this evening for a session full of action packed learning. And I am Siddharth, part of the data science team at Analytics Vidhya, and I'll be the moderator for this session along with Priya. So, for those who have joined us for the first time, a brief introduction to the DataHour sessions. So, guys, the DataHour is a series of webinars conducted by Analytics Vidya and led by top industry experts. It's a fun way to understand the concepts of data science from the leading players in the data tech domain, as we have Anant today with us. So, guys, as the name suggests, it's 1 hour dedicated to data. We are hopeful that these sessions are going to be a great source of enrichment and value adding for our community members. So now on to our session today, which is introduction to optimization problems for data scientists. So guys, now I'll be elaborating this topic like the session for you. So suppose you are Amazon. If you were to decide the most efficient delivery route for your delivery partners or the inventory amount of a certain product to be stored across different warehouses, so how would you go about designing a data science solution that ensures efficiency and at minimum costs? So this data is going to introduce you to a very important AI technology, which is mathematical optimization that solves mission critical business problems. We'll walk through the basics of optimization, discuss real world examples, and solve a business problem hands on in Python. So, guys, before we kick things off and I hand it over to our speaker, a quick recap of the housekeeping items. So we are recording this session and we'll make the recording available in a few days on our YouTube channel. And please use the Q&A section for any questions you might have during the session. And we'll do our best to answer them as the data progresses or towards the end. And also we will share a poll about the feedback of the session towards the end of the session, which I request you all to kindly fill up. Now guys, on to our speaker in this session of data, we have Mr. Anant Agarwal. So Anant is a data science manager at Nissan's Global Digital Hub. He's an IIT Kharagpur alumni. He received his MS on a full scholarship from University of Minnesota, USA, and MBA from Indian School of Business, Hyderabad. He has worked briefly at an edtech firm in San Francisco before joining Nissan. He is also a national level squash player and a fingerstyle guitarist. So, guys, now over to you, Anant. The virtual stage is all yours.
Thank you for that introduction, Siddharth,
Yeah.
and welcome everyone to this data hour. So let me start sharing my screen.
Yeah.
I am unable to start my video. Siddharth, can you check whether it's enabled?
Yeah, just a second. Can you try it now?
Yes.
Yeah, it's done.
Yeah, great. Okay. Hello everyone. Welcome to this webinar or introduction to optimization problems. I am Anant and I'll be taking you through the foundations of optimization theory. And then after that, we will solve a real life business problem in Python through some of the most popular techniques that organizations look for when they hire optimization scientists. Like Siddharth already introduced me, I work as a data science manager at Nissan, and I started out my career as a data scientist at Lofty in San Francisco. So without further ado, let's get started. So before we dive into the main agenda of today, let me talk a bit about why I chose this topic and why I chose to talk about optimization, right? Because we have so many fascinating topics. We have machine learning, we have visualization, we have statistics, but why optimization of them all? The reason is that in the data science curriculum, optimization is not taught so much, and looking at the graduate coursework in the US programs and also looking at online courses, right? Optimization is not popularized a lot. But if you look at the industry scenario, optimization is used to solve a lot of good problems. And those problems are very complex, data heavy, and they add a lot of business value to the stakeholders, right? When we compare this against machine learning, optimization also has certain advantages that I will be going over. But the main idea why you should care about this session a lot is because optimization would give you a competitive advantage in the competitive job market, right? So that's a good reason to learn about optimization. And my goal here in today's session is to walk you through the basics and also give you a flavor of what it is like to implement it in Python, right? So we'll not just look at theory, we will also look at the practical side in Python. So I'll be talking about the overview, the foundations of optimization, mainly looking at linear programming in a lot of depth. Then we will look at a use case transportation optimization, which is a leading example of how optimization adds value. And then we will be looking at the Python implementation in 5 popular tools. So let's define optimization. Basically, there are 3 parts, right? Optimization is looking at a certain set of decision variables. So it is looking at things to optimize for, right? The target is the objective that we want to optimize. So for example, if I want to reduce costs, right, that is my objective of the entire exercise. And I also have certain constraints that I need to withhold, that I need to basically satisfy. So optimization refers to finding the optimal solution for an objective subject to a certain set of constraints, right? If you think about your daily life, we have a limited amount of time, right? And there's a limited amount of effort that we are willing to put in certain tasks. So you might have noticed we pick certain tasks up and we do not want to do other tasks, right? Because we are again optimizing for the value that we are getting out of them. So it works similarly in business scenarios as well. In operations research specifically, optimization involves creating a digital twin. A digital twin basically means a virtual representation of the actual operating environment, right? Once we create a virtual representation of the actual operational environment, we can understand how to optimize the operations, right? We can understand, how to reduce the failure of assets and how to improve the process time, the process lead time it takes, using a detailed mathematical model. So underlying everything is a mathematical model, which we refer to as optimization here. One question that comes up frequently is, why do we want to do optimization, right? We have computing power. We know that, machine learning and neural networks can learn very complex underlying distributions and relationships. Then why do we want to go for a mathematical model? One of the main reasons is that machine learning predicts a particular value, right? It doesn't work well for interconnected decisions. So when I do one thing, it affects how I can do the other thing. Because if you remember, we have constraints also with us. It's not unconstrained, like we don't have unlimited resources. So we want to optimize for a particular objective subject to a limitations, right? And that's where machine learning also falls short. And for making complex interconnected decisions, where if we do one thing a certain way, that affects how we can do the other thing and so on, machine learning is not as capable as optimization, right? So that's one particular area where optimization is good. The other area is that machine learning solutions also suffer from model drift, right? If you recall this term, this basically means that the data is changing over time, right? That is bound to happen over time. And the relationships between the explanatory variables, right? The things that we are observing and the target that we want to predict for, the relationships also keep on changing over time. So that's called a model drift, right? And machine learning solutions are susceptible to these. But optimization is a bit more robust to these, right? So that's another reason why optimization can add more value in this context. All right. Let's look at optimization as an analytics field, right? Here we are talking about decisions. So if you look at the y-axis, it is talking about decision making in an organization, right? The far top is proactive decision making, and the bottom one is reactive decision making. So after a certain set of events have already occurred, then we are reacting to that and we are trying to understand what has happened. So if you recall, when we look at historical data, what we do is basically descriptive analytics. We want to look at certain variables, say sales, the expenditure that we did, the profits that we got, and competitor events and so on. And we want to understand what has actually happened. So those are standard reports basically, right? Those are of low complexity. If you see the far left x-axis, then we go on to ad hoc reports, which basically say that, if you don't understand something in standard reports, we want to do ad hoc analysis and then go on understanding what has happened. Then going a bit deeper, we get into query drills. A bit deeper, we go into alerts. So when a similar thing happens in the future, we want to create an alert system, right? And slowly, if you think about it, we are moving towards proactive decision making. When we create alerts, we are basically saying if it happens again in the future, we want to be alerted about it, right? As soon as it happens or as soon as a certain parameter changes. Then to the more familiar territory of statistical analysis, right, which is basically diagnostic in nature. It tells us why a certain event occurred the way it did, right? We look at hypothesis testing, we do t-tests and so on, and understand what is actually happening, right? This can also include causality, for example, like we can do Granger causality tests and so on. Those are all diagnostic in nature. Then we move on to predictive forecasting, right? So predictive analytics includes forecasting and other methods, but basically it's saying that what will happen into the future. So now we're not thinking about the past anymore, we are thinking about the future, right? And it is adding more value if we just compare it to descriptive analytics. And finally, we come to prescriptive analytics, right? Which is the field of optimization. What prescriptive analytics is saying is, what kind of decisions should we make so that we optimize for our objectives. So say we maximize our profit, what are the different kinds of levers that we should keep, what are the values for those levers we should keep in our organization, right? So if we think about it, profit is driven by sales, right? The more sales generally that you have, the more profit you will get, keeping other things constant, right? For example, yeah. So if we are looking at maximizing profit, sales is also dependent on how much we are spending on advertising, how much our competitors are spending on advertising, and so on. So the way in which we can do optimization is we can build a model, we can build a machine learning model to predict sales and predict profit. And then we can look at, using that model, we can try to optimize for our profit. We can basically say, spending more than say $100 a month will not help us increase our sales. So why spend say $200? Let's cut down that extra $100, keep our costs low so that our profits are maximized, right? So machine learning and optimization can go side by side. But if you're talking about optimization, it adds the most value and it is a proactive decision-making approach. And it's highly complex. For example, compared to machine learning systems, optimization systems take a lot of work to build up upfront, whereas machine learning systems take a lot of time to stabilize, right? Once you build an algorithm, you need to keep retraining it, keep refreshing the models, and keep monitoring, right? So there's a lot of work laid out into the future, but optimization does all the work upfront. So there's a lot of upfront work that you need to do. So that's kind of a trade-off that you need to think about when you're thinking about optimization problems. And one more thing is, when we get a business problem, the business stakeholder doesn't point it out whether it's a predictive problem or it is an optimization or a prescriptive problem. That solutionizing lies to the data scientist to think about how does he convert a business problem into a data problem. Once that is done, how does he take the data problem, split it apart and figure out what kind of methods and techniques to use to solve that problem. And then he stitches up the solution and then presents it back to the business stakeholder, right? So probably you might not, or a lot of people have not heard of optimization, but taking business problems, optimization is very common, right? And it's very commonly applied. Now let's talk about the hype cycle, right? So this is the Gartner hype cycle curve, which gives a view of how a technology or application will evolve over time, right? Whether it will not be as useful or whether it is just a hype and it will, fall down very badly and it will not be news anymore, right? Whether it will survive at all. etc. So there are 5 different aspects of the hype curve, right? There's a technology trigger which basically triggers the adoption of the technology, right? We can say that a technology trigger for machine learning and deep learning would be the computing power, right? Due to which they slowly started getting more popular in the last 2 decades, right? So right now, if you see on this chart, machine learning and deep learning are at the peak of inflated expectations. So inflated expectations basically mean that there is a lot of hype around these technologies, which might not all be true, right? They certainly add value, but if you say that they can add value in unrealistic scenarios, or they always add value, that might not be a right thing, right? There are certain prerequisites for machine learning and deep learning to also work, and there are success stories, but there are also failure stories, right? And that also lies more towards the operational side of how they were deployed, how they were built, how flexible the systems were, and so on. But there is definitely a peak that we are seeing for these two technologies and related AI technologies, right? After which there is a trough of disillusionment. So naturally, if there are inflated expectations, we might not be able to fulfill all of them. But after that comes the slope of enlightenment that basically says that these technologies become more and more mature. People understand, how to build them and use them and deploy them. And then there's a plateau of productivity. So if we talk about mathematical optimization, right, if you can see the timeline on the bottom, these technologies go far back into 1940s, right, when simplex method was first developed. And then dynamic programming was developed in the 1950s. In the 1960s, roughly geometric and nonlinear programming were developed. So basically optimization field was evolving because you can see nonlinear programming being developed, right? So nonlinear models, as we all know, are more complex models. So when we are developing nonlinear programming techniques, that means the optimization field is evolving over time. And lately simulated annealing, evolutionary algorithms, and so on are also developed in the 2000s. So mathematical optimization reached the peak in 1970s. Actually, it reached the trough in late 1970s, and it has been at the plateau since 1990s, right? So that's probably one reason why it is not so popular, but it definitely is very useful. Further, optimization is everywhere, right? It is there across a lot of different fields. So it is there in supply chain, it is there in finance, sales and marketing, and so on. But the majority of applications lie in supply chain, right? Because operations need to be optimized so that the cost is reduced. If we just talk about in very layman terms. Now let's talk about the use cases in supply chain. We have truckload capacity optimization, right? Basically, this is saying that a truckload is in a particular truck, how much load can we put, and think of certain parcels, right, that you need to fit into a truck. Each parcel will have a certain capacity and it will have some sort of a value associated with it, so that if you transport, you will get a certain value. Let's just think of the value of that parcel, right? So what we want to do here is, with a limited amount of capacity, we want to optimize for the value that we are transporting, right? It might seem simple, but there are a lot of trade-offs involved, because a truck follows different routes, right? Different trucks follow different routes. There are different demands for those items on those destinations where the truck is transporting to. So there are a lot of factors which affect what kind of parcels, what quantity of parcels should be loaded onto the truck, right? That is truckload capacity optimization. We come to inventory optimization, which basically says that what is the right amount of inventory we need to keep with us so that all the demand for the product is being met, the logistics costs are low, and stockouts are not occurring, when the stock is finished. Overstocking is not occurring when we have too much of stock, so we are facing storage costs, and back orders are not occurring, right? So that's inventory optimization. Inventory optimization is a very widespread use case. It is used in e-commerce, right? If you think about Amazon, Flipkart, and so on, they all want to optimize the inventory that they are keeping for a certain product. We can also think about OEMs like, car manufacturers. They are also looking at inventory optimization. Now let's come to production optimization, which basically says what is the right amount of production that we should do, right? And there are a lot of different factors similar to inventory optimization also involved here. So this is basically about production control, and shipment routing is another very good use case of optimization, which is basically saying, you know, what is the best route for a particular shipment to go, right? If we are looking at a particular set of destinations, so if a shipment has to go from point A to B and there are different stops in between, which of those stops should it take, right? It is not a matter of the smallest route, right? So there are a lot of different factors involved. So the main idea is to find the best routes for a fleet of vehicles visiting a particular set of locations. And a very popular problem, which is a textbook problem, is the traveling salesperson problem, which says find the shortest route for a salesperson who needs to visit customers at different locations and return back to the starting point, right? So what is the route he should take to visit all those customers? And definitely he needs to reduce his costs, optimize, and so on. So now we have talked about supply chain. Let's now come to finance, right? And one of a very good use case in finance is portfolio optimization. When we are talking about portfolio, it basically means we have certain assets with us, right? Or we want to build and keep certain assets with us so that we can maximize our returns. So what is the portfolio of assets that we should keep with us so that the overall portfolio's return is optimized and it's maximized for us? So there are again trade-offs involved here because assets are very risky as well. So depending on the risk appetite of a customer, the portfolio manager would then go forward and recommend a particular asset to him or her, and then the customer will think whether I should keep it in my portfolio or not. Right? In sales and marketing, there is revenue optimization. So price is a lever. If you increase price, demand is bound to go down. But depending on the elasticity that the product has in the market, there is a trade-off involved there as well. So price into demand, which is price into the demand, it's the final revenue that you are getting, right? So if you increase price, demand will go down, but will it go down by that same percentage? Will it go down by a lesser percentage, or will it go down by a higher percentage, right? So there's a trade-off, and as long as the demand goes down by a smaller percentage than the price has gone up, then we are basically increasing revenues, right? And it's a good thing to do. So revenue optimization is a very important problem that is solved in sales and marketing departments. And then there are other applications such as workforce scheduling, which is basically saying that if we have hourly workers in our industry, then what the schedules of those hourly workers should be so that the current and future demands of that workplace are met, right? It can be a restaurant, for example, where you have waiters coming in during different shifts. It can be a hospital, it can be a retail store, and these problems can become very complex if they are scaled up, right? So that's where optimization comes to the rescue. In electricity distribution and in vaccine distribution also, we can think of COVID-19 vaccines, right? We have a limited amount of vaccines. Which population subgroups should be prioritized? Should it be healthcare workers, elderly people, and which cities should be prioritized first? Where the number of deaths are occurring more, should they be prioritized more, and so on. So there is a limited set of vaccines, but where should you transport them, and how should you route them? Like through what route should you take them? And there are many more applications. All right. Now this is the main crux of today's session, which I would request all of you to pay attention to very much. So we are going to be talking about linear programming, and a few of you might have already encountered this concept, but my idea here is to give a more in-depth introduction to this particular technology, right? So let's start with the preliminaries. Yeah. I can see a raised hand. So I would request for the questions to be at the end so that the flow is not broken, and we can take all the questions at the end. Till that time, if you want, you can put the questions in the chat window, or you can also keep them noted down and we can take them at the end. All right. So let's look at the preliminaries of optimization. We have an objective function that is the outcome metric of interest, right? And it also has the optimization goal in it. So should we minimize the objective or should we maximize the objective? We have decision variables, which are basically a set of unknown variables that control the value of the objective, right? So if you just think of the very simple example, we have a limited amount of time and effort, and we want to maximize our value, right, that we get out of a day, the happiness, for example, that we get out of a day. Those are our decision variables, that in what activity should we put more of a time in, what kind of effort should we put in that activity, right? So that, you know, overall we get a better sense of well-being, right? So those are our decision variables for a very simple personal example. And the constraints are that, you know, we have a limited amount of time and effort that we can do in a particular day before we get tired. So there are the limits on the decision variables, and they allow only certain values for the variables to be take. So this is an example. We want to maximize y here, which is 5x1 plus 8x2, right? This is our objective function. The objective here is y is equal to 5x1 plus 8x2, where x1 and x2 are some variables subject to these three constraints, right? And these are all lesser than equal to constraints. So two of them are lesser than equal to, and the third one is a non-negativity constraint, which is basically saying the variables should be positive. Now let's talk about some of the optimization techniques that are very popular, right? The first one is linear programming. What a linear programming optimization technique says is that the objective must be a linear function of the decision variables, and the constraints also must be linear in nature, right? So that's the prerequisite for a linear programming optimization problem. And if you want to use this particular algorithm to solve such problems, then these prerequisites should be satisfied. For nonlinear programming, it's basically saying that the objective or any of the constraints are non-linear with respect to the decision variables, right? And where basically linearity is not there. So if I multiply two decision variables, say I am looking at time and effort. So if I multiply time into effort, and that's my objective function, that's not a linear representation in terms of the variables. It becomes non-linear, right? So then linear programming will not be able to work. In that case, we look at non-linear programming, and then there are different kinds of non-linear programming methods, right? So there is geometric programming, in which objective and constraints should have a specific form. There is dynamic programming, right? So dynamic programming is basically doing a top-down approach. It is breaking down a particular problem into different segments, and then it is basically solving each of the sub-segments separately and then combining the result, right? So that is a better approach than simply doing a recursion, and it's less costly. Then we look at integer programming. So integer programming basically says that all the decision variables should be integers in nature, right? We are looking at stochastic programming, where we are saying there is a bit of uncertainty involved, right? And then we are looking at evolutionary algorithms and simulated annealing and so on. So these are very advanced nonlinear programs. So today's session, we will be talking about linear programming. All right. Let's start with a particular linear programming problem. Before that, let me take a pause and let me just check if we have any particular questions. Okay. All right. So one question by Sylvia is about if profit is objective function, right? What does decision variables refer to? So in this case, if we are looking to optimize for profit, right? Decision variables are basically, you know, how much spend should we do for a particular product. So you can think of advertising spend. Should we be spending a lot on advertising, is that actually converting into the demand, or is it going to waste? So if the excess advertising spend is going to waste, we want to reduce that so that we can maximize a profit, right? So the amount of advertising spend can be a decision variable because we are making that decision, and there can be other decisions as well, right? For example, choosing a particular vendor, right? What vendors should we choose so that we can maximize our sales and so on. Yes, we can apply graph theory for shipment routing. Yeah, that's right, Rishabh. Sure, I will share some books and GitHub repos. You can contact me later, and I will share some, some resources as well. Okay, let me take the last question at the end. So let me continue. So let's take an example problem, right? Suppose a custom molder has one injection molding machine with two different dies to fit the machine. So the machine can fit two different dies, right? One die is basically for 6-ounce glasses, and the second die is basically for 10-ounce cocktail glasses, right? So this is the setup, and now we have a certain set of constraints. Before that, let's look at the problem statement. The problem statement is basically saying how many cases of each type of glass should be produced per week in order to maximize the total contribution, which is the total profit, contribution profit, right? And we have certain constraints. 100 cases of 6-ounce glasses require 6 production hours. 100 cases of 10-ounce cocktail glasses require 5 production hours, right? So there's a constraint on the basically how many production hours are required to produce each of these glasses. Then we have production capacity. A limited set of production capacity is available per week, which is 60 hours in this case. Then we have storage capacity. Effective storage capacity is available of 15,000 cubic feet, where one case of a 6-ounce juice glass requires 10 cubic feet of storage space, and a case of 10-ounce cocktail glass requires 20 cubic feet of storage space. We also know the contribution, that is the profit of 6-ounce glasses, is $5 per case. Contribution of 10-ounce glasses is $4.5 per case. And we also have information about the demand that available customers will not accept more than 800 cases per week of 6-ounce glasses. And 10-ounce glasses can be sold as much as we want. Okay. Now let's think about structuring this problem. We have a fair bit of idea about the constraints, right? We also know what is the objective, which is the total contribution, right? So let's start the problem by looking at the objective. We want to maximize the total contribution, right? What is the total contribution? The total contribution is the number of 6-ounce glasses to be produced, right, multiplied by 5 plus the number of 10-ounce cocktail glasses to be produced multiplied by 4.5. Right? So this is the total contribution. This becomes our objective, right? And this should be maximized. Let's, for simplicity, because we have the production hour constrained in 100 cases of glasses, let's keep the decision variable as 100 cases of glasses, right? So the objective function, let me just bring the slide up. So x1 is saying the number of cases of 6-ounce glasses in hundreds, and x2 is saying number of cases of 10-ounce glasses also in hundreds, right? And the total contribution then, if these are our decision variables, will be 500 x1 plus 450 x2. So we are multiplying this by 100 because our decision variable itself is in hundreds. So it is 100 glasses is x1. So the contribution of 100 glasses will be 500 for each x1, each unit of x1, right? So that is our contribution. The production capacity, we are looking at 100 cases of 6-ounce glasses requires 6 production hours, right? So this is 6 multiplied by x1, the first decision variable, plus 5 multiplied by x2, which is the second decision variable. And the total production capacity is 60 hours, right? So this basically says 6x1 plus 5x2 is less than equal to 60. So this is a production capacity constraint in this case. Let's look at storage capacity constraint. We know that a case of 6-ounce juice glasses requires 10 cubic feet of storage space, and a case of 10-ounce cocktail glasses requires 20 cubic feet, right? So if we are talking about in hundreds of glasses, this is basically 1000 of x1 plus 2000 of x2. We are multiplying it by 100 because we are talking in hundreds of cases. So 1000 x1 plus 2000 x2 is less than equal to 15,000, right? And when we simplify that, we get 10x1 plus 20x2 is less than equal to 150. Demand is less than equal to 8 because we know here that 6-ounce glasses demand will be less than 800 cases per week. The customers will not accept more than that. So it makes no sense to produce more than that, right? That will become x1 is less than equal to 8. And then there is a non-negativity constraint. So once we have this problem, now let's try to solve it using a graphical technique. All right. We basically go ahead with plotting these particular constraints. So the first constraint is the production capacity constraint, which is 6x1 plus 5x2 is equal to 60. We plot this in a 2D graph, right? This is the line. So the feasible region lies towards the origin, which is to the left. The non-negativity constraints say that x1 and x2 should be greater than 0. So this becomes the region. If we include the storage constraint as well, right? 10x1 plus 20x2 is less than equal to 150. Since there is less than equal to sign, right? The origin would be included in this particular constraint, because if we put 0, 0, then that will be less than 150. So we are looking at this shaded area now, right? If we include the storage constraint. And finally, once we include the demand constraint, x1 is less than equal to 8, this becomes a feasible region. Okay, let's talk about infeasibility, right? Infeasibility is basically saying that we are not able to find a region, any region that is satisfying all the constraints. So in this case, if x1 was greater than equal to 10.5, if we had such a constraint, you can see that, you know, with respect to these 5 constraints, there is no feasible region that satisfies each of these constraints. So this is an infeasible region, and an unbounded region is one where the region exists, but it is unbounded, right? So it is very difficult to find the actual objective value and the optimal solution. One caveat here is we are looking at a maximization problem, then this becomes an unbounded region, right? Because if in a maximization problem, as x1 and x2 increase, the objective value will also increase, right? And that's what we want to do. So here, as we go towards the top right to infinity, the objective value will keep on increasing, and that's what we want. But on the other hand, say we had the same region, but the direction of the objective was opposite, it was a minimization, then this would not, this would still be solvable, right? Because the objective will hit one of these vertices, and then that would be the optimal solution in that case. So we will talk about why a vertex corresponds to an optimal solution. But basically, if this is a maximization problem, this becomes unsolvable. So these are two unsolvable scenarios. Now let's try to solve the problem, right? We don't get too bogged down by this chart. This is the feasible region. One addition that we have done here is we have added the objective equation, right, which is 500x1 plus 450x2, and this is the particular line that it will look like, and this is equal to alpha, right? So what we are doing here is basically we are just plotting this line. This is called an isoprofit line. Let's take a random value, which is say 1000. In that case, the line will look like this. If we want the profit, if we increase the profit, overall profit, to 2000, the line will be having the same slope, but it will move outwards, right? So it will look something like this, and so on, right? So as if you look at the middle chart, right, as we shift out the line, right? So the first one is 980, this is 1960, this is 2940, where the total contribution is 2940. This will be the line, right? If we keep shifting this line out, it will hit a vertex of the feasible region, right? Why that is the case? Because the feasible region has certain vertices, right? And this slope is bound to hit any of these vertices. So when it hits the vertex, that is our optimal solution, because it cannot go more away from there, right? Because the feasible region will stop existing if we move more towards the far right. And if we keep being in the internal feasible region, then that's not the maximum profit that we can get. The maximum profit is basically going from 0 0 to infinity infinity, right? It's moving that way. So this is our optimal solution, and this always leads to a unique optimal solution. There is one caveat, that if the objective line, right, the objective function itself is parallel to one of the constraints, then there might be multiple solutions, right? So for example, if we were looking at 225 exponent plus 450 x2, this was our objective function, right? And this was parallel to this storage constraint, then we will have infinite solutions, but we will always have a solution at the vertex for a linear programming problem, right? All right. Now let's come to binding constraints and non-binding constraints. So this is the feasible region, right? Wherever, whichever vertex we find as the optimal solution, whatever constraints are contributing to that vertex or are touching that vertex, those are the binding constraints, right? So if you look at this storage constraint, right, we cannot so the storage capacity of 150 is exhausted here, right? And similarly, if you look at the production constraint, this capacity of 60 is again exhausted here. So this is a binding constraint. But if we look at demand, right, which is x1 is equal to 8, x1 actually here is just 6.43, right? It is somewhere only at 6.43. So it is not exhausted. So this is a non-binding constraint, right? It can still increase the demand, the value for x1 can still increase in this particular case, right? This constraint is not sufficiently exhausted. If we have a less than equal to non-binding constraint, in the case of demand, for example, x1 is less than equal to 8, then there is a slack associated with it, which is basically saying how much x1 can still increase. That is, the demand slack is 1.57, and the surplus is basically saying if we had a greater than equal to constraint, right? Say x1 is greater than equal to 10, that was a constraint, and the value that we got at optimality was 12, then we basically would say that the surplus is 12 minus 10, 2. That is, we can still use up 2 units before, the constraint is reached. We are not able to reduce it further. So that is a surplus associated. So this was an overview of the basic terms involved in optimization. Now let's look at sensitivity analysis, right? So this was a one-time exercise, but in business scenarios, there is no scenario where if you just implement a solution, it stays that way, right? So you need to keep monitoring it, you need to keep improving the system, and business decisions need to keep changing. So sensitivity analysis helps us understand the trade-offs involved. In this case, production capacity has been exhausted, right? Now, if you want to think about, let me invest into increasing the production time by 1 hour each week, and let me see how much profit am I able to get. How would I go about doing that, right? Without actually putting in an extra hour of production and then going 1 week out into the future and looking at it. How would I understand that mathematically through the solution that I have built? So I will look at sensitivity analysis, and I would change one thing at a time and measure its impact on the optimal solution. So there are 3 important concepts: shadow price, allowable range of the objective coefficients, and reduced cost. All right, just 5 to 10 minutes more, and then we will be through this core foundations of optimization, and then we will look at Python. I know this is heavy, but this is very, very important to understand optimization in detail. All right, let's look at shadow price. What shadow price is basically saying, the question that we are looking at is we want to increase the production capacity by 1 hour each week, and we want to see the impact on the contribution that we are getting, the total objective value that we are getting, right? Definitely, if we increase production capacity, the objective value will increase in this case. Why is that? Let's look at it graphically. So this line here is the storage constraint, and this line here is the production constraint, which is 6x1 plus 5x2 is 60. We want to now increase it to 61, right, by 1 unit. So this constraint will become this red line here, right? And if you look at the storage constraint, we can extrapolate the storage constraint, right, through this arrow, which is shown here. So the new intersection of the storage constraint extended and the new production constraint will be this particular red value, right? And this will be a new optimal solution of x1 and x2, right? And in this particular vertex, the objective value, right? So the objective value was 500 x1 plus 450 x2. So 500 x1 plus 450 x2 will have a different value than it had at the earlier vertex, right? So that is a change in the total contribution, the total objective value that we are seeing. Everything else remaining the same, we just increased the production capacity by 1 hour. The optimal solution changed and the objective value also correspondingly changed. So the shadow price is basically saying what is the change in the optimal value of the objective per unit increase in the value of the constraint, everything else remaining the same, right? Similarly, if you want to decrease the production capacity and then see how much the contribution is changing, we basically say 6x1 plus 5x2 is 59, and this is the new vertex, and this is the new objective value corresponding to this vertex, and we can just take the difference. One thing to note about shadow prices is that they are constant over a range, right? So the range is defined as the set of binding constraints should be the same. What that means is, for our problem, if we are looking at the shadow price of the production constraint, the set of binding constraints originally that we started from was the storage constraint and the production constraint. Now these two set of binding constraints should always remain binding. They should not become unbinding, right, or non-binding. Here what is happening in the first scenario, the production constraint is binding but the storage constraint is not binding. How you can think is, what we have done is the storage constraint was somewhere around here where my laser pointer is showing, and it is slowly moving inside towards the origin, right? So it has completely left off the storage constraint, and now the optimal vertex has become on the non-negativity constraint of x2, number of 10-ounce glasses, right? So shadow price will be different now, right? Because if we change the production constraint by a little value, say if we increase it, the new vertex will move vertically up. Right now it is at x2 is equal to 6, it might be x2 is equal to 7, right? That might be a new vertex. And you can think of the objective function, only x2 is changing here, x1 and x2 are not changing. So the objective function will also change differently with respect to the previous case where the set of binding constraints remain the same. So the shadow price changes if the set of binding constraints also changes. Second figure is showing when the shadow price will remain the same. So the production value can become 37.5, right? So this will be the line, and it can also become 65.5, right? So this is the line. So between 37.5 and 65.5, the shadow price will remain the same. And this is another extreme case where the storage has become binding, but the production constraint has become non-binding, right? So this can also happen. Some mathematical relationships are that slack or surplus into shadow price is equal to 0, right? For a binding constraint, there is no slack, but so slack is 0, but shadow price is non-zero for a binding constraint, right? Like we discussed. If it is a binding constraint, if we change that little bit here and there, the objective value will also change. So the shadow price is non-zero. but the slack is 0 because it is already exhausted, right? So for a binding constraint, this will be 0. Now let's look at a non-binding constraint. For a non-binding constraint, the shadow price will be 0, slack will be non-zero. The reason why shadow price will be 0 is, let's look at this example here, right? This is the demand constraint, right? If we increase it or decrease it, it doesn't really matter because it's not playing a role in finding the optimal solution. It is already in excess. So if we increase it further or decrease it a little bit, more than the optimal solution, so it will not matter. So shadow price will be 0. So this always holds. And there is another formula for optimal objective value. Now let's look at the contribution, right? The objective coefficient. So I have two sets of glasses. Both are giving me certain amount of profit. Now, if the amount of profit that one glass is giving me is changed, right? Will the optimal solution still remain the same? Will I still want to produce a certain quantity, the same quantity of that particular glass, even if its profit has changed? The answer is yes, but there's a caveat that it remains the same within a particular range of profits. So if you think about changing the profit, right, we are looking at an original line, right? This is the original line, 500x1 plus 450x2. If the profit is changing, say for x2, the coefficient is changing. So it becomes from 450, it might become 550 to 650. So what that is basically saying, the slope of the line is changing, right? So in this case, for example, what it is showing is the profit for x1 has increased. Initially it was 500 x1, now it is becoming 1500 x1. So the slope of the line has changed, right? And it has changed so much that the optimal solution has also changed. Now we should only produce 800 glasses for x1, which is 6 ounce glasses, and 240 glasses of 10 ounce glasses, right? So the solution has changed. But in this second case, the second graph, we can see how much the slope can change so that the optimal solution still remains 643, 429, right? 643 units of 6 ounce glasses, 429 units of 10 ounce glasses, right? So this is the another way we can understand how sensitive our optimal solution is to the objective coefficient. And finally, we want to look at reduced costs, right? So I want to understand that if I'm producing a particular kind of a glass, is it valuable for me at all? Should I produce it or not? So there's an opportunity cost involved, right? When I'm producing it, it is taking up certain production hours, it is taking up certain storage. So if the opportunity cost of producing a unit is higher than its contribution, it is not attractive to produce it. And the net marginal contribution is called the reduced cost, right? It's basically saying that if I increase the production of a profitable glass type, then obviously my contribution will increase because the glass is profitable, right? The amount of resources that it is taking to produce that glass, that is less than the profit that I'm getting from selling that glass. So it is profitable to basically produce that glass. And the marginal contribution is also in terms of, if I would have dedicated the same resources to the production of another glass, would I have had more profit, right? So there is a trade-off involved, also looking at other production of glasses. So that's where the reduced cost concept comes in. All right. So now, till now we have looked at linear programming. We have understood the basic concepts of linear programming, and we have looked at certain, we have looked at certain concepts like feasible region. We have looked at infeasibility, unboundedness. We have also looked at sensitivity analysis, where we have looked at shadow prices, allowable range for objective coefficients, and reduced costs. So these are very important concepts, and I took a very simple problem to explain these concepts. Now let's look at a use case, and let me give a brief background about transportation optimization. So as the name suggests, right, Transportation optimization is basically the process of gaining efficiency, right? It is ensuring optimal routes, that the routes are optimal, and basically you are minimizing the expenditure that you're doing on transporting the freight. And the idea is to remove the empty miles of the supply chain, right? So that you're ensuring that no vehicle is going empty, or there are very few number of vehicles that are going empty on a particular lane or a particular route. There are three steps: procurement stage, planning stage, and execution stage. And each of these stages of transportation, right, there are different use cases that can be built through optimization to reduce the overall spend, right? So in the procurement stage, basically the shipper, we can think of Amazon, it wants to, it's supplying a certain set of commodities and it wants them shipped, right? In the procurement stage, it is looking at certain carriers also that basically transport goods, right? So it wants to basically assign a certain set of carriers for a particular route and a certain other set of carriers for other routes. So how does it procure those carriers? Because each of them will have different codes and rate information. So here Amazon can simulate the transportation spend to evaluate carrier bids, right? We can think of another company which basically is evaluating carrier bids. Amazon also has its in-house delivery service, so I think it will be more appropriate to take example of another company which is evaluating carrier bids. Then there's a planning stage where the shipper needs to identify future capacity requirements with respect to the demand, right? And it runs what if simulations for fuel costs and so on, right? So that's the planning stage. And then there's the execution stage where we can talk about truckload optimization, right? Build efficient loads by taking into account loading priority, right? Which parcels are of higher priority, which ones are of less priority, what is the weight. So there is also a certain guideline on the amount of weight that a truck can take. So the weight of each parcel also needs to be taken into account when we are thinking of building an efficient load. The cube, which is the volume of that particular load, the quantity, number of parcels, and then consolidating less than truckload shipments into truckload shipments. So sometimes it is more efficient to have less than truckload shipments, right? And sometimes it is better to have truckload shipments. So looking at the trade-off between those two, that also comes in the execution stage. And there are several benefits that you can think of. There is increased delivery capacity, efficient use of labor, right? There are less labor hours because they spend less time in planning of routes and so on. Cost savings are there. Customer experience is better because they are getting parcels faster and they're not paying extra for it. And then also for drivers, the routes are optimal, right? So there is reduced overtime. They are working for a lesser number of hours and they are getting the same job done. So there are a lot of benefits. Let's look at another problem, right? So here what we are seeing is we have a set of supply cities. We can think of these as warehouses also. So A, B, and C are warehouses, and these are the locations or the retailers where the items need to be transported, right? This is the demand city. So D, E, F, G, and H are the demand cities. So the numbers in the matrix basically say the shipping cost from A to D is 16, A to E is 7, A to F is 17, and so on. And the capacity of the supply city A is 70, right? It's in thousands. B is in 50, C is 30, and so on. And the demand that can be expected, the maximum demand for the retailer D or the demand city D is 30. For E, it is 24, and so on, right? So the goal is to basically ship to all of these 5 markets, or we can think of these as retailers, at a minimum total shipping cost from these supply locations. So they are supplying the same product, and that needs to be shipped to these 5 different retailers from these 3 warehouses, and each of these have a different shipping cost associated with them. So how do we formulate a problem, right? Let's start by thinking about the objective. What is the objective here? The objective is basically the number of shipments from A to D multiplied by the shipping cost, that is 16, plus the number of shipments from A to E multiplied by the shipping cost 7, and so on for 15 of these particular scenarios. So A to D, A to E, A to H, these will be 5, B to D, B to E, B to F, B to H, these will be another 5, and so on for C. So we have, it will be, the objective function will be a summation of these 15 products, right? So I've elaborated it a bit mathematically, but this is what it is basically: Cij into Xij, where Cij is the cost of shipping from I to J and Xij is the amount of shipments that we are basically shipping. And if we just sum it up, that's the total cost. That's our objective. Now, looking at the objective, we understand that what is in our control is the number of shipments, because the costs, shipping costs are fixed. We already know that, right? How do we determine the number of shipments that we do so that the total cost is minimized? And this also looks at a certain set of constraints, right? The total supply for any location should be less than the capacity, right? So this will be a set of 3 constraints. The demand has to be greater than equal to, so this is the demand, right? So the demand that is generated should be greater than equal to these particular values, right? For these cities, these will be 5 constraints, right? So we are looking at minimum demand actually here, and this is the maximum capacity, right? So these are the minimum demands. So the demand has to be greater than equal to the minimum demand. And then there are non-negativity constraints, where we are basically saying the number of shipments have to be greater than 0. So there are 15 different kinds of shipments. If you look at supply demand combination, so there are 15 constraints. So this is a total of 3 plus 5 plus 15 constraints, which is a set of 23 constraints. And there is this complex objective function, which is a summation of 15 products of values, and there are 15 decision variables in our particular problem. Now think of the decision variables, right? How are the decision variables? What is the nature of decision variables? Are they continuous variables? Are they real numbers? No, they are integers, right? The number of shipments has to be discrete. It has to be 1, 2, 3, etc. So this becomes an integer programming problem, because all of the decision variables take integer values only, right? But otherwise the constraints and the objective function, those are linear in nature. So this is the field of integer programming, and this is significantly more difficult than linear programming. Why that is the case? Let's think of a particular simple problem, right? If our goal is to maximize 3x1 plus 4x2 subject to this constraint, and this is the feasible region that we are looking at, right? Now the optimal solution no longer lies at the vertex, right? Because the possible solutions are the ones that are highlighted in the dots, right? These are all integer values. It cannot be a decimal, right? So it cannot lie, for example, here. It cannot be 4.8 comma 0, right? So the optimal solution here is at 3 comma 1, right? And the algorithm has to figure that out by looking at all of the possible integer combinations and then evaluating each of them. In a linear programming problem, what the algorithm can do is it can just look at the vertices, fit them into the objective function, find out the objective value, and then find out which vertex corresponds to the optimal solution, because we already know that the optimal solution will lie at the vertex, but here that is not the case, right? And before we dive into the Python implementation, this is what the optimal solution will look like. From A to E, there should be 24 shipments. A to G, this is the number of shipments, and so on. And we also get a priority order. So this we can infer from the final solution that we are getting, right? There's a lot of inference at play here, but what today we are concerned about is just finding how we get to the solution, right? Once we get to the solution, we can also infer the shadow cost, or sorry, the shadow price, the reduced cost, and the allowable range for the objective coefficient, looking at this priority order. So this gives us a lot of information about what is happening behind the hood in this particular transportation problem. Okay, let's dive into the Python implementation of the problem. We'll look at 5 different tools, right? And we'll use all of these to basically solve the same problem and we'll get the same solution. So the idea is to get you familiar with the syntax of the different packages which are available. Jurobi and Ciplex are commercial solvers, so they are state of the art, but they are not open source. So there is a caveat there. They were very powerful. Pulp is an open source platform, so it is another very good library which can be used for linear programming. We have scientific Python library, right, which is also open source as we know, and we have Google OR tools, operation research tools as well. So now let's go on to the hands-on workshop, and let me paste this link in the chat. All right. So what you need to do to basically run this is you need to have a Google account which you can log in, right? And when you open this particular link, you will get this particular notebook, right? Which you can run on your own system, right? So this is running on the cloud. So let me start from the beginning, right? The linear programming problem formulation is, this is what it looks like that we discussed, right? So this is the objective function which is composed of 15 different components, 16xAD, which is basically saying number of shipments from A to D multiplied by the shipping cost of 16 and so on, subject to 3 supply constraints because we have 3 supply locations or 3 warehouses and each of them have a particular capacity that they can store, right? So the supply capacity, we have 3 constraints, and then there are demand constraints, right? Because we have 5 retailers or 5 demand cities, and what we are saying is that the minimum demand that needs to be fulfilled is 30 for this particular uh, demand city. So here the demand city is D, right? So A is supplying to D, B is supplying to D, and C is supplying to D. So the total number of shipments that are coming to D must be greater than equal to 30. And this gets repeated for the other 4 locations as well, the demand locations. So this is a set of 5 constraints, and then we have 15 constraints where the decision variables have to be greater than equal to 0, and they also need to be integers, right, which is not mentioned here, but that is implicit in the program. What you can do now, and I'll wait a few seconds for it, is you can set up the environment. Basically, you just need to run the this particular cell. So you can press Shift Enter, right? And what it will do is it will basically run pip install using the notebook, and it is basically doing that on the command line. That's why the exclamation is there. And once you have run this, make sure that you're going to runtime option in the collab notebook and you are clicking on restart runtime. The reason why we are doing this is because OR tools gets loaded only after you have restarted the runtime. So after you have installed, make sure you are going to runtime and clicking restart runtime, and then starting with importing the libraries. Okay, let's restart the runtime. It is restarting. Okay. So it has imported all of these libraries now. Now in this simple scenario, what I've done is I've just input the data manually here into three different variables: supply, demand, and the cost array. The supply is basically saying for the supply city A, this is the maximum capacity of 70 and so on. It's a dictionary object. For demand, it is another dictionary object, and the cost array is basically a 5 by 3 matrix, right, which I have manually encoded. The rows correspond to the supply locations and the columns correspond to the demand, right? We run this and I'm just checking if the shape of my cost array or the shipment cost matrix is the same as row column of supply and demand. Now let's look at the implementation of this optimization solution in Jirobi. So the first step is to initialize the model, create a model object. What I have done here is I have imported this library as grb. So grb.model, this object is basically the linear programming model that I am initializing. Then I'm defining the decision variables. Generally what we do is we create a dictionary for the decision variables in this manner. So it is basically saying I comma j, this is the key in the dictionary, and the value is, what we are doing is we are adding a variable to this model object, right? So Jirobi underscore lp underscore model dot add variable, the type of which is integer, and the name is basically what it is saying. It is the supply location hyphen the demand location, right? So this is what it is saying, basically list of supply dot keys and I, because this becomes a list, right? So I and j for I in range length of supply. So this goes from 0 to 2, and j in range length of demand, which goes from 0 to 4, right? So this is the quantity array, the decision variable array. Now let's look at the constraints.
So sorry to interrupt.
Yeah.
Actually, we are running out of time, so we should wrap it up fast.
Sure, I'll take another 5 minutes and we should be good.
Yeah, thank you so much.
Yeah, thank you. All right, let's look at the constraints. So the constraints, basically what we are doing is for I in the range of length of supply, right? So because this is 3, we have 3 constraints. We are adding constraints using this particular method, add constraint. What we are doing is we are saying what we need to do in the quantity array is basically we need to sum up the demand from all the locations for that particular supply location, right? That is one row in the matrix. We are saying we are summing that up, and we are saying that should be less than equal to the capacity of that supply location. Similarly, we are going to the second row. We are adding up all the shipment values for that supply location. We are saying that should be less than equal to the capacity, and so on. So this is for the supply, this is for the demand similarly, and this is a non-negativity constraint. So let me run this quickly. Right, our objective function is nothing but the cost array multiplied by the quantity array, the number of shipments, and I am just doing a for loop inside itself, and the objective is to minimize it, right? So I do this and then I click on optimize. So it has optimized it, right? Now what we can see is I formatted it, and we know that the optimal shipments from one city to another city is this value, right? So from A to E is 24, from B to D is 12, and so on, right? So this is one result that we get, which was depicted in the solution, right? And we can also get the shadow prices and the reduced costs. Similarly, if you run simplex, right, the syntax is a bit different, but the overall idea is the same. We again create a quantity array, the same variable, using a different method, right? And we add the supply constraint, demand constraints, non-negativity constraints, the objective value, and we again solve the problem. So from A to E we observe 24, right? So this is the same solution. We can do the same in pulp, right? We are again following the same procedure, and we get the same results. Now let's look at SciPy implementation. This is a bit crude. So what I had to do here is I had to create a matrix, right? Because it works only for arrays. So I'll not discuss in depth how I created this, but this is what the constraint matrix looks like, right? So we have 15 variables that we are looking to optimize. These are the coefficients for those variables for a particular constraint. So this is basically saying I have taken the order to be AD, AE, AF, AG and AH are the first five variables. So they have value 1 here, which is basically saying everything which is originating from A, the sum of that should be less than equal to 70. The second row is another constraint and so on. So these are 23 constraints which are shown in this matrix. The number of rows is 23 and the number of columns is 15. So let's run this and see the answer that we get. So once we solve this, we again get the same result. We use a linear programming method here. And lastly, let's look at Google OR optimization, right? So I have reused the matrix from the SciPy implementation, defined the decision variables, the constraints, right? I'm getting a status here, whether the problem has been solved or not. And finally, I am optimizing it. So what you can do is after the webinar, you can go through this at your own time and let me know if you have any questions. And yeah, that was it for today's session. Thank you so much, and I'll be happy to take any questions now.
Okay, thanks a lot, Anand. That was a great session, and I hope all our attendees found it really helpful. So, guys, before we proceed to answer your questions, I would like to request the attendees to please fill in the poll about the feedback. The feedback poll is already live. You can just participate in it and fill the poll. And after that, we'll take questions. And guys, you can put your questions in Q&A section. Anand, we can start taking the questions. Yeah.
Okay, so one question was around why are we taking, let me go to that slide. Yeah, so in this particular example, can x1 and x2, do they need to be integers, right? So in this case, that is not the case, right? Because we have defined the variables to be in hundreds of values, right? So this is hundreds of classes. So they can take at most 2 decimal places. So that's why what we have looked at here is 6.49 or 6.43 and 4.29. We have actually approximated this integer programming problem as a linear programming problem, right? Actually, it is an integer programming problem. Yeah. So that was the first question. In all these suggested methods for Python implementation, can implementation vary? This question is by Rutuja. So the implementation definitely varies because each of these have different methods, but the overall flow, right, that we adopt, that remains the same. The flow changes a bit in SciPy optimization using linear programming and also in Google OR tools, but overall it does remain the same. Okay. Yeah, implementation time is something to look at. So the Jirobi optimization and also the Simplex, these are the fastest ones. Please explain how a linear programming problem differs from a non-linear programming problem using the concept of time versus effort. Okay. Okay. So this will be a little bit abstract in a way, right? Because we are talking about time and we are talking about, how it will be a non-linear programming problem. But if we think of a constraint that we have in the case of time, right? We have um, 5 set of activities that we want to denote our time to, right? And the total time that we have is say 24 hours. We do have that much time. The amount of time that we give to a particular activity, uh, it might not be linear, right? The relationship might not be linear. Okay, I think this is not a good example to explain the difference, but the basic idea behind non-linear programming problem is that in the constraints that we are looking at, we are basically looking at a non-linear constraint, right? So the decision variable itself is becoming squared, for example. So say 6x1 squared plus x2 is less than equal to 50, where x1 and x2 are the decision variables. So if we have this kind of a non-linearity, then it becomes a non-linear problem. Okay, can we solve this issue with machine learning model? We can use machine learning and optimization both. So machine learning will help us learn the relationship between the decision variables and the objective, right? In this case, what we did is we basically just took a sum, right? We are saying 5x1 plus 6x2 is the final objective function. But in many cases, we do not actually know this formulation. We do not know how the decision variables are impacting the objective, right? So if you are spending a certain amount of money, how that is going to impact sales. So to learn this relationship, we use machine learning. But once that relationship has been learned, we then use optimization to maximize the objective. So we can add machine learning to the mix. In practical world, how complex could it get to conceptualize, design, and operationalize an OR model? And how is it brought into production? In practical world, OR models are very complex. There are a lot of variables, and they are brought into production in a similar manner to machine learning models. So they also need to be monitored, although less, and it takes a lot of upfront time because the number of variables in real world systems are very large, right? If you're looking at inventory optimization or if you're looking at truckload optimization, the constraints that your business has for your specific business needs, you need to change the business needs into constraints and then solve the problem. So the entire process from getting the requirements, converting them into your constraints, then looking at different techniques, looking at the runtime required, whether it is feasible enough to run all the complex algorithms or should you start with a simple algorithm, coming to a decision on that, and then finally operationalizing and making sure that the result that you're getting is in line with what you should be getting. So that takes a good amount of time. So the end-to-end time is similar to what a machine learning system would also take to finally stabilize.
Yeah, hello. Yeah, hi Anand.
That's all, I think.
Yeah, actually, I think we are past the time, so
Sure.
we'll be wrapping the session now.
Sure, Siddharth. Yeah, I think I'm
Yeah,
good with all
thanks
the
a lot,
questions.
Anand.
Yeah, thank you.
Yeah, yeah, yeah. So, on behalf of Analytics Vidya, I would like to thank you for your time and for delivering such a wonderful session. I am sure our audience found it insightful, and hopefully, we can conduct more such sessions with you in the future.
Definitely, I'm looking forward to taking more sessions, and please
Yeah,
keep in touch.
yeah, we will.
Yeah,
Surely.
thanks a lot.
Yeah. So, guys, we have already mentioned Anand's LinkedIn profile in the chat section, so you people can connect to him over there. And I hope you guys have filled the feedback poll. If not, I request you to please fill in the poll about the feedback. Thank you, Anand. Thank you so much.
Thank you. Have a-
So, guys, the recording of this session will be available in a few days on our YouTube channel. And we'll be back with another session of data around 12th of August. So, the link is in the chat section. Till then, bye bye and keep sharing.